So I'm going to answer your question, but I want to talk about how we do this with degrees first. Okay, so let's say I've got this theta here, this example 3 from yesterday. Example 3 says, find an angle with measure between 0 and 360 as coterminal with the angle of 1290 in standard position. Now, the homework question you said now says find one positive coterminal angle, one negative coterminal angle, right? Or something like that? 2 positive, 2 negative. 2 positive, 2 negative. What this process is going to do is going to get one of our angles that is between 0 and 360. You want basically the smallest version of this angle. And then we can use that kind of logic to maybe help with your question. So right now, 1290. So what's going on here?
Which equation do we use?
I'm going to talk to you about it. Relax. So 1290 degrees. So this would be one revolution. Well, let's do this in a different color. So I've got, there would be one revolution. Does that make sense? That's 360 degrees. This would be a second revolution. That's another 360 degrees, right? Do this green one. This is a third revolution, right? Yeah. Okay. So I'm 360 times 3, right? Yep. Okay. Which is 1080, correct? Yep. Okay. So now the remainder that I need to go to get to 1290 would be that amount right there, which that red amount is 210 degrees. Does that make sense? Yeah. Okay. So my terminal ray for this, my terminal ray for 1290 degrees is that blue ray right there. Remember, this is my initial ray, right? No. Okay. Initial, and this is terminal. Okay, so here's the question. Can I find an angle that is going to have the same essential features as 1290, but is a lot easier to deal with?
Probably.
Well, the way we do that, and it's the red angle there, but the way we do it is we take 1290 and we start subtracting away from it multiples of 360, where k is essentially an integer. Okay? So I'm going to take 1290 minus 360 when k is 1 and see what that gives me. Is it giving me a number between 0 and 360? If it does, great, that's my answer. If it doesn't, I keep going. I change k to 2. Does that make sense? The easiest way to do it is to grab your technology, whatever calculator you want to use. I'm going to go 1290 minus 360, hit enter. So that's not between 0 and 360, right? So I'm going to subtract another 360, hit enter. Now here's a nice feature about your calculator. Once you've used answer minus something, if you just hit enter, it will do it again, okay? So that's not between 0 and 360, but that one is. Does that make sense? So 210 degrees is the answer that I'm looking for. That is the angle, I'm going to call it alpha. That is the angle between 0 and 360 that we're interested in. So alpha is 210. Is that okay? Okay. Now here's where this is going to kind of go and why we're doing this. Now you don't need to write any of this down, but I want to make sure that we kind of understand this. Eventually what we're going to be interested in is finding sine, cosine, and tangent, secant, cosecant, cotangent, the 6 trigonometric functions, evaluated at 1290, okay? That can be kind of nasty, and the goal is to be able to do that in our head and be able to say, okay, I know the sine of 1290 is negative 1/2, and know that right off the bat, and this is how we go about doing this. So I just want to kind of, I think it makes sense in classes, especially classes that you haven't had any background with, to the things that we're doing right now to see where this is taking us, okay? If you go back to like 3rd grade when you're learning how to multiply, maybe it would have been nice when you're learning how to multiply, you're learning your individual facts, to be able to see, okay, where am I going to use this down the road, okay? Maybe when we're writing equations in 9th grade math, maybe it would have been nice to know, okay, where am I going to use that down the road? How important is learning writing equations? And then maybe we would have taken it a little bit more seriously when we got to that stuff, right? Does that make sense? So, you know, hindsight's 2020. We always hear that, right? Hindsight's 2020. Yeah. It's nice to have a little bit of hindsight as we move on with stuff. So I want to give you a little bit I want to show you something so you see where it's used, and then that should hopefully provide us hindsight to the stuff that we're working with now. So here's where this is going to lead to. I'm going to ask you, what is the sine of 1290? Okay, and I'm going to take your calculators away. okay? Because obviously our calculator will do that instantaneously for us. And this is the route we go. The first thing we do is we're gonna figure out, say, okay, well, we don't like 1290. So we're gonna find an angle that is between 0 and 360 that matches 1290. So if I look at that ray and that ray, where this angle here is 210, if I overlay those two things, the initial ray and the terminal ray laying on top of each other, right? So 210 and 1290 give me the same information. Now, so basically what I'm asking or telling you then is that the sine of 1290 is going to be the same thing as the sine of 210. Does that make sense? Yep. Okay. And all the other 6 trig or other 5 trig functions will be the same thing. So if I want to do cosine, or if I want to do secant, cosecant, cotangent, tangent, they're all going to be the same. Okay. So the cosine of 1290 is the same thing as cosine of 210. Secant of 1290, same thing as secant of 210, and so forth. Now here's where this kind of starts to incorporate maybe some other things that we're going to learn here in the next couple of days. We still don't like to deal with 210. Okay? We don't like to deal with 210. If I look at that angle right there that I'm just going to color green, how big is that angle? Maybe you can't really see. So if I start, let's just do it in red.
You're talking about 180?
Yes. That angle there is 180 degrees, right? So how big then is that angle? Which is 30. Okay? Now, what we're going to do, and it doesn't matter where you do this, because this ray goes on forever, but I'm going to, at some point on this ray, I'm going to put a point, and then I'm going to draw a line that goes perpendicular to the x-axis. Do I get a right triangle right there?
Yes.
Okay. So get a right triangle, and that right triangle has a 30-degree angle in it right now, correct?
Yep.
Means it also has a
90 and 60.
Okay. Now, here's the thing. We know stuff about special right triangles, right? From geometry. And it doesn't matter what this distance here is, okay? Let's say this distance is 5, then that one's 10, and that one's 5 radical 3. You guys remember going through that stuff 2 years ago?
Yeah.
Okay. So I'm just going to say, I don't really care. I'm not going to use 5. I'm going to use n, 2n, and n radical 3. You guys remember that kind of setup? Okay. Now, sine and SOHCAHTOA, sine represents what? What's SOH represent? Sine
over hypotenuse.
Is opposite over hypotenuse. So sine right now of 30 degrees would be n over 2n. Does that make sense? Okay. But this n, that distance right there, is representative of that distance right there. And if I'm in the coordinate plane, this distance right here, to go from 0, 0 to that point right there, what direction do I have to go in the y direction? Up or down? Down. So shouldn't this y value right here be negative? So that n is negative. So sine, in this case of this 30 degrees, what I'm looking for is negative 1/2. Okay? So what this is getting, and so you don't obviously have to write all that down, and we'll talk about that in a much more greater detail later on. But the next couple sections are going to slowly build to our ability to say that when they give me sine of 1290, I can automatically, without my calculator, say that that's going to evaluate to negative 1/2. And you should be able to justify this with our calculator then. Okay, if I take sine of 1290, make sure you're in, what mode do I need to be in if I'm sine of 1290 degrees? Okay, so I hit sine of 1290, does it give me negative 1/2? Yes, okay. So eventually we should be able to do this. You know, if I type in cosine of 1290, okay, we should know that, okay, so cosine is adjacent over hypotenuse, right? So adjacent over hypotenuse would be, in this case, n radical 3 over 2n. So it's going to be radical 3 over 2, which is 0.86 something. and it should be negative because it's in this distance here on the x-axis should be a negative. So negative 0.86. Okay. So we should hopefully maybe be able to do those things, kind of rattle those answers off eventually very, very quickly without the use of a calculator. Is that all right? Now the reason we're doing that is because when we're in trig, we want to be able to do things with exact values. Okay? We don't want to use the negative 0.866025438. We would rather leave that as negative radical 3 over 2, because when we use it for another calculation later on in another application trigonometry, working with that exact value will make the work in the algebra so much easier. So what we try to do is we try to develop these skills to be able to do this. And that's what this first couple weeks is going to be about. Yes, please.
Are you actually going to do that thing where you take away our calculators and we have
Oh, absolutely.
So can we talk about that question?
So Blaze had the question, if we are looking at
5 pi over 4.
5 pi over 4,
2 positive angles, 2 negative angles.
and we want 2 positive coterminal and 2 negative coterminal, right? Okay. So right now 5 pi over 4, if we think about where that's at, okay, this is 0 degree, so 0 radians. This would be pi radians, right? 180 degrees. Does that make sense? This would be pi over 2. This would be 3 pi over 2. Does that make sense, everybody? Going around. So pi over 2 is 90 degrees. Pi is 180. 3 pi over 2 is 270, right? Okay. Well, pi over 4 would be halfway in there, right? So that's pi. That right there would be pi over 4. This would be 2 pi over 4. That's another pi over 4, right?
Yes.
There's a third pi over 4 right there. There's a fourth pi over 4. 4 pi over 4. Think about this. 4 pi over 4. What's that reduced to? Pi, right? So 5 pi over 4 would be that angle right there. Does that make sense? Okay. And again, we're going to eventually talk more about that, because really these problems aren't getting us to draw this picture, but I want you guys to kind of see how I know that when I say 5 pi over 4, I know it's in the third quadrant here. Okay. So that angle right there, that angle is what his problem is starting off with. Does that make sense? Okay. They want to know, okay, how far do you need to sweep this angle out again? So start with that ray right there. That's your terminal ray for 5 pi over 4, right? This was your initial ray. How far do you need to sweep this ray so that it gets back to where it started? Okay, 360 degrees, but are we working with degrees right here?
No, we're doing pi.
So we're working with radians. So what is equivalent to 360?
2 pi.
2 pi. So what I'm going to do is I'm going to take 5 pi over 4 and add to it 2 pi. Well, 2 pi with a denominator of 4 is 8 pi over 4. Does that make sense?
What? Oh.
Fourth grade fractions.
Yeah, I'm not gonna fix
All right. So when I add those, 12, that gives me what? 13 pi? 13 pi over 4. That's my first positive coterminal angle with that, right? Okay. Add another 8 pi over 4 to that. That's going to give me 21 pi over 4, right? Those are my two positive coterminals. How do I find negative coterminals? Subtract 8 pi over 4. So then I get negative 3 pi over 4. Okay. And then we'll subtract another, so that's one of them. We'll subtract another 8 pi over 4, so negative 11 pi over 4 would be my two negative ones. That make sense? Okay. So now this is what some people like to do. And this is fine. It's just more time consuming. Okay. But think about this. If I've given you a tool to convert radians to degrees.
Yeah, you give us that equation.
Okay. So if I've got 5 pi over 4 and I want to change that to degrees, can I multiply that by 180 over pi? Pi's cancel, right?
Yeah.
4 cancels there, gives me, what, 45? 5 times 45. 225?
225, yeah.
Okay, is that correct? Everybody good with that? Okay. Now, if I want to find, so instead of asking, okay, coterminal angles with 5 pi over 4, it's essentially asking what are the coterminal angles with 225. So now what could I add to 225 to get a coterminal angle? 360.
I tried it this way.
Okay. So, well, hold on. 225 plus 360 is what? 585, right? Okay, did you type 585 in?
Yeah.
What's the direction say?
It needs to be the other way.
Needs to be in radians, right? So now I need to undo the conversion that I did at the beginning and change back into radians, okay? So now 585 divided by 180, 585 divided by 180 will reduce to 13 over 4, and then I got my pi there. Is that answer right there? That makes sense? But my hope is that you recognize doing it that way is safe. And there will be times, guys, in this class that working with radians is nasty for the thing that we want to work with. We don't like it. Maybe it's, and I don't want to say nasty because of the arithmetic on the math. It's nasty because of us not being familiar with it. Some people are going to say, okay, every time I see a radian, I'm going to convert it to degrees and do the work with degrees. Does that make sense to them? Okay? But then once they have an answer in degrees, they need to remember, oh, it started with radians. So they're going to want their answer in radians. So now I got to unconvert it, right? Or convert it back. And those 2 steps might be an additional 2 or 3 minutes that we don't want to waste eventually. Does that make sense?
Yes.
Okay. All right. You know, I do that when I'm trying to find rates of things. Like if I want to find, if I'm working in a problem that says kilometers per hour, and I don't know, my car isn't a kilometer per hour car. I don't know what it feels like to go a kilometer per hour. So if I'm working on a story problem, and when I'm done, I look at my answer like, does that really make sense to the context of the problem? What I'll do is I'll take my answer and I'll change it to miles per hour. I'll change the other values in the problem miles and hours, and I'll look and say, okay, does the answer in miles per hour make sense to the problem in miles per hour? And if it does, then it tells me that my answer in kilometers per hour probably made sense to the problem that was written in kilometers. Does that make sense? I like to transfer things, unit-wise, to things that I'm comfortable with, so I can make arguments about, yeah, it makes sense, no, it doesn't make sense, and I can have some justification for my answers. So that's kind of what you could do there. Now, there was a question on there that said something like this. It said, find an angle if theta is equal to, let's just say, 14 radians.
All right.
Find an angle between a coterminal angle between 0 and 2 pi. Okay? This is what the people get thrown off in this, and I think that they're making it a little bit more difficult than what they're trying to get at here. If it says 14 radians, okay, the pi that we normally see with radians, and this is where people get confused. Normally, when it's a radian measurement, it has pi somewhere in it, right?
Yep.
Okay. Well, the pi here has already been multiplied through by whatever the coefficient of pi was, and it just by happenstance gave me 14. Does that make sense?
Yep.
So really what this, an alternative version of this would be that theta is equal to 4.45633840657 pi.
How'd you know that?
I just know everything.
When's my birthday?
Okay. March 13th.
March 11th. That was so close. How did you know that?
So 4.45633840657 times pi, if you type that in your calculator, you're going to get 14. Does that make sense? Okay? So the pi is already in there. So just make sure that we are comfortable with when seeing that unit and pi isn't written, that means it's already been multiplied through. It's already been simplified for us. Okay? And they usually only do that if it simplifies to a whole number. okay? Or maybe a decimal that terminates or whatever, okay? So here we've got 0 is less than, alpha is less than 2 pi. That's what we want a coterminal angle that is between those two numbers, okay? Now, when this doesn't have pi in it, what I like to do is instead of looking at 0 less than pi, or sorry, 0 less than alpha less than 2 pi, I like to do this. Would you agree at 2 pi is approximately 6.28? 3.14 times 2, right? Okay. Is 14 between those two numbers? No. Okay. So 14, okay. So this 14 radians, so this would be a little, this would be 2 pi, right?
Yeah.
That would be 4 pi, okay. Maybe that would be about 4.45 pi. Does that make sense?
That's a lot.
So that might be 14 radians right there, okay, all the way around that many times, okay? Well, I want to find an angle that is the same as that, but between 0 and 6.28. So how do I get back to that spot? How do I take this ray
Subtract 2 pi.
and move it back one complete revolution back to where it started? I'm going to subtract 2 pi. So I'm going to take 14. I'm going to take 14 minus 2 pi, and it gives me that number there, right? Is that between 0 and 6.28?
No.
Nope. So now I'm going to subtract 2 pi again. And it gives me 1.43.
Yes.
Okay? Is that between 0 and 6.28? Okay, so that's my answer, 1.43. But if you look at your homework has absolutely no directions. It says, find a coterminal angle between 0 and 2 pi for 14 radians. Doesn't say round to 2 decimal places, doesn't say round to 3 decimal places, doesn't say anything like that. So when it doesn't say, what does that mean to us? Can I just haphazardly say 1.6 or 1.63 or 1.633?
No.
So what do I do?
Change it to the other one.
What do you mean the other one?
Rad.
No, it's already radians. I didn't do it.
Change it to degrees.
No, I'm talking, it doesn't tell me how to round it. It doesn't say what decimal place.
Put everything in there.
So if it doesn't tell me how to round it, what does that mean? Exact value. It means don't round it. So the exact value here would be
What number is that?
14 minus 2 pi one time, but then didn't you subtract 2 pi a second time? So isn't that what they want you to type in is 14 minus 4 pi?
What
Okay.
number is that?
And that then is that 1.63 number as an exact value. I'm not sure what number it is, somebody brought it to me earlier today.
This?
I think it's towards the end maybe. Does that make sense though?
I think it's like 31.
Okay. And you're going to see kind of those types of instructions throughout the rest of the year. If it doesn't tell, if you do the work and you get a decimal, and obviously because we're using pi, okay, any product of pi is irrational. Any difference between or sum between two numbers in pi is going to be irrational. So you can't round it. Okay, or you can't let it terminate. So if it doesn't tell you how to round, then the assumption is it doesn't want you to round. Okay, and you gotta type in the exact value. Is that something we can do?
Yep.
Okay. Do you guys remember? Do you guys have any other questions on that stuff right now? Huh?
31.
What's 31 say?
23 pi over 6. Find an angle between 0 and 2 pi that are coterminal with the given angle.
It says
3 pi over 6.
23 pi over 6. Okay. Now you want two coterminal angles?
Find an angle between 0 and 2 pi that is coterminal with the given angle.
Okay, so 0 and 2 pi. Okay. Would you agree? Okay, so if I look at this, I'm always going to put, so that the angle that I'm asked about, I'm always going to put this 2 pi in terms of that denominator. So would you agree that 2 pi is the same thing as 12 pi over 6? So 23 pi over 6 is above that, right?
Yes.
Okay. So what do I need to do with this 23 pi over 6 to get it down less than that number? Subtract what? 2 pi. If I subtract 2 pi, that's subtracting 12 pi over 6, right?
Yep.
What's 23 pi minus 12 pi? 11 pi. Is 11 pi over 6 fall inside that interval?
Yes.
Yeah, so 11 pi over 6 is my answer.
That's the answer. You know, on WebAssign, if you just type in PI, it automatically goes pi. Okay.
You have any other questions you want me to do?
Want to help it with? Now I can figure out that one. No, I think we're chilling.
All right, good. Got a question for you. Do you remember geometry?
Yeah. I remember Tyler meant to pour a bottle of water in my bag, and you did nothing about it.
You know why?
Did you hate me?
I didn't like you then either.
Hey, Cole trying to tell me that you got hops.
I got what?
Hops. There was no way.
Yeah.
He said, quote unquote, for your size, you can jump pretty high. Which I did not believe it.
You got like what, 40 years?
Chuck that as chump. I think about to jump 50.
Well, that's only 2 more inches.
Hey.
All right. Do you remember, and from your previous comments,
I don't think you can get 40 years.
what in the world?
I don't think you can get 46 years.
All right. If we look at this, the task in the next couple questions is going to be, can we find this number here that they're asking about? Can we find the arc length? Okay. So if you remember back to geometry, we had a formula for this. And what we need to do is we need to know what that angle right there was. And I'm just going to call that angle theta. Okay. If you remember, okay, isn't this theta, back to geometry, that theta is equivalent to the measurement of that arc as a degree. You guys remember that? If this theta was 30 degrees, this red arc was 30 degrees. Remember talking about that?
Yeah.
A central angle is equivalent to this, in regards to it, a measurement, okay? The arc measurement, the central angle is equivalent to the subtended arc, okay? Now, when I say the word subtended, all that means is it's the arc. So I've got that ray right there, and I've got that ray right there, right? Okay? If I didn't have this circle here, I would just have that set of rays, right?
Yes.
To close that ray off with that one, we're going to make a smooth curve. And that smooth curve then would be that right there. Does that make sense?
Yes.
So that we say that arc subtends these 2 rays or subtends the angle. Okay, so we're essentially talking about the arc that is made by these 2 rays. Is that all right? Okay. So some people get kind of crossed up with what that definition is. If I want to find that, okay, I want to find that arc length, we have to figure out what theta is. And that thing then, isn't that arc, or that central angle, or that arc, isn't that a portion of the whole circle?
Yes.
Okay? So if this is degrees, then can I take that theta and divide it by 360 and see what percentage, essentially as a decimal, that angle is of the whole thing, of 360?
Yep.
That makes sense? Okay? So let's just say if that theta was 60 degrees, I can take 60 divided by 360, and that angle would be 1/6 of my triangle, right?
Yes.
60 divided by 360, okay? That means then that arc is also 1/6 of my circle. Does that make sense?
Yeah.
But it's 1/6 of my what of my circle? Circumference, okay? So this here is going to give me the fraction that this is of my circumference. So if I take 1/6 times 2 pi r, that will give me the length of this arc, right? Does that make sense? Okay? So we did that in geometry. Great, awesome, it worked. But what we find out here is that a lot of our previous formulas with angles involved are a little bit more complex than they need to be. Okay? So let's do this. When we talk about arc length, okay, the letter we use for the symbol is lowercase s.
For arc?
For arc. Okay? I don't know if that stands for subtended or I'm not sure what the S stands for. But that's what we generally use. Okay? So we know it's theta over 360, okay, if we're in degrees, times 2 pi r. Okay? I'm going to rewrite that because I think it's just going to make a little bit more sense. Can I write that 2 pi r all over 1?
Yeah, you can.
So I'd have theta times 2 pi r over 360, right? Okay? Now that would mean that my theta right now is in degrees. Is that okay with everybody? Because it's at 360 degrees. Let's change it to radians. In order to get that 360 to cancel out, I need to multiply by 180 degrees over pi. That will get these 360s to cancel, right? Let's think about that. If I take 360 and 180 and cancel, it's going to leave me with a 2 on the bottom, right? What's going to happen with that 2 on the bottom now? It's going to cancel with the 2 on top, right?
Yep.
What's going to happen with the pi on top?
They're going to cancel.
That pi cancels with that pi. What are you left with on top then?
Zeta r.
Theta r. That's your formula for finding arc length when theta is represented in radians. Would you agree that that formula is so much easier to remember and so much easier to use?
Yep.
Okay, but we got to remember that theta is going to be in radians. Okay, so when they asked us this first question, find the length of an arc of a circle with a radius of 10 meters that subtends a central angle of 30 degrees. Okay, so what we're saying here, we've got a 30-degree angle, so maybe that's 30 degrees. Okay, and we want to figure out how long is that arc. We're going to find that S. Okay, well, we know the radius is 10 meters. Okay, now if I go S equals R theta, what does theta have to be in?
What? Radians.
Theta has to be in radians. What is it in the problem? Degrees. Anybody remember from what we did the other day what 30 degrees was in terms of radians? Pi over 6.
Whoa.
Okay, now we will see that so much that that will be, as easy as 2 plus 2 for you. Okay, but if you can't remember that, can I have gone 30 times pi over 180? The 30 and the 180 cancel, giving me pi over 6, right? So now R was 10. Okay, theta is pi over 6. So we get 10 pi over 6 as my answer. Now, it's a distance, right? Okay, when we ask the arc length, that's a distance. Well, what was 10's unit? Meters. It's meters to the first power, right? What was pi over 6's unit?
Degrees.
Radians. Okay, so when I do this multiplication, I might think that my answer should be meters times radians, right? Have you ever measured a distance as meters times radian?
Never.
No, you've never seen it. You've never seen a meter written with a radian after it, right? That doesn't happen. And the reason for that is that radians, by definition, are dimensionless units. And I'll show you here, if we have time today, if not tomorrow, that explanation. But whenever you get in your answer other units along with radians, I just want you to kind of cross the radians out right now because they're dimensionless. Okay? And it's based off the definition of what a radian is. It's a length of an arc divided by the length of a radius. That's the measurement, or that's the definition of a radian. Well, if I take a length in feet divided by a length in feet, what happens to the units? They cancel out. So when I talk about radians, I'm really only talking about the number. Okay, and we only use RAD to make things clear about what that number is attached to, what it goes with. Does that make sense? So if I just say 3/2, or pi over 3, or pi over 6, you don't know what I'm talking about. You don't know what that's attached to. When I say pi over 3 radians, oh, he's talking about an angle. Does that make sense? Okay, but it doesn't have a dimension. Okay, so our answer here would be 10 pi over 6 meters is the length of that arc. Okay, if you used, and I'm just going to do this real quick on the side, but if you use the geometry formula, arc length is equal to theta over 360 times 2 pi r. Okay, theta was 30, right? Divided by 360 times 2 times pi, r was 10. Okay, what's 30 divided by 360? 1/6 times 20 pi, right? Is there a 2 in both those? Is that what we just had? No, we had 10 pi over 6. What did I do? 2 pi r. Oh, yeah. 30 divided by 36 is 1/12. My bad.
No, you're good.
1/12. Okay. So then 4 cancels in both those, right?
Yep.
Okay, so that's going to leave me 5 there. 3 there.
We need to simplify the other ones.
Yeah, we're gonna simplify. So I'm having a moment. So 5 pi over 3, same thing is 10 pi over 6, right? We're gonna simplify this. Okay. So you can do either route. My hope is though maybe that you're thinking about having both those at your disposal, and if you don't like to convert radians into degrees or degrees into radians, you just use the appropriate one based on the measurement or the type of measurement they give you. Okay. This one's working a little bit backwards. They tell you the central angle is theta. You've got a radius of 4, and the arc is 6. And they want you to find theta. Well, what things relate arc and radius? If this is S, this is R, and that's theta, don't we have a formula that says S is equal to R times theta?
Yep.
If I know S, if I know R, and I'm looking for theta, 6 divided by 4 should be theta, right?
Yes.
Or 3/2 is theta. Now here's the thing. This 6 and this 4, maybe they were in feet. Maybe they were both in inches, maybe they're both in miles, whatever. But when I divide them, I get 6 over 4, right? And that's it. Feet divided by feet goes away, right? They cancel. So we get 6 over 4 or 3/2 equals theta. That must mean, so I tell you the number is 3/2, but you don't know, if I just say 3/2, nobody knows what that's attached to, right?
Right.
Well, because it was an arc divided by a radius, you know, by definition, that 3/2 is a radian. Okay? So that's kind of how maybe that unit, when I answer this question, that unit pops up as radian. Okay? Where in the last question, the radian disappeared. Okay?
Call it a day.
Can't. This formula is the same idea. We talked about area, right?
Yep.
Okay. So area in geometry was this. What's the area formula for a circle?
1/2 pi r squared.
Just pi r squared.
Pi r squared.
Okay. So that's the area of a sector, right? Those slices of the circle. But if I want to change this to radians, can I multiply by that? What's going to happen with the 180 and 360?
Take some stuff out.
Cancel, right? What happens with the pi's? Cancel. And what I'm left with now is pi, no, sorry, not pi, theta, times r squared all over 2. Does that make sense?
Yeah, and that's for when?
And they take the 1/2 out and write it that way. But that's finding the area of a sector. So remember, sector is just one of these slices of your circle, right? Okay. If I want to find the area of that, if theta is in radians, that's the formula I use. So in this question here, it says find the area of a sector. So with this picture here, maybe the area of that sector right there, where this central angle is 60 degrees. Anybody remember what 60 degrees was in radians?
1/4 pi.
Nope.
Pi over 4.
Pi over 3.
Dang.
Okay. So we go 1/2 r squared, which was 3, times pi over 3. Okay. Now this was meters squared, right? Because m or r was 3, so I square it, I get meters squared. This was radians, right? When I multiply this all out, so those are going to cancel, give me 3, right? So I end up with 1 times 3 times pi, which is 3 pi. On the bottom, I'm left with 2 times 1 times 1. So we get 2, right? Units are meters squared radian. When I'm done with this, now think about this, I'm finding the area, right? Have you ever written an area as meters squared radian?
No.
No. What happens to that radian?
Drops.
Drops out. It goes away. Vanishes. It's dimensionless. It doesn't hold any water in regards to labeling our units. Okay? Tomorrow, guys, and in the last class talked about this, but tomorrow we're going to introduce this idea. Okay? If I take a object on a string, a weight on a string, okay, and it doesn't matter if it's a weight on a string, if it's a seat on a Ferris wheel, if it's a tooth on a saw blade, it doesn't matter. A blade on a fan. When I start swinging this thing, what shape do I make?
Circle.
1, 2, 3 people are looking. Okay, I'm swinging this, right? We've got a circle. Okay, is that so? If I do this, that mouse isn't going very fast, right? But I can speed it up, right? So we're talking about the speed of that mouse. Now, when you talk about speeds or velocities, you are more accustomed to talking about them moving that way, right?
Yep.
Okay. So what we can do is we can take the speed that this thing is going, and we can convert it to what it would be doing if it was going this way. Because here, it's not gaining any distance, right? We're not covering any ground. But we can do this. You guys have like digital speedometers on your car. Tell you how fast you're going in digits, like instead of the tach. Okay. There are sensors in your wheel bearings. Okay. That essentially tell how fast your wheel is oscillating, and then does the math in the computer of the car and generates what that number is, that speed is, on your dashboard. Does that make sense? Yep. So when you see a speed, it's really not saying this is, it's not calculating that I've gone from point A to point B in the time that it took to do that and then dividing it by that time. It's simply taking the speed in which that wheel or that sensor is being kind of tracked as the wheel goes around. I'll explain that a little bit more in detail in that technology. But if I look at this thing right here, okay, this mouse, let's say that cord is the positive x-axis. That's my initial ray. As I move the mouse, that would be my terminal ray, right?
Yeah.
There's an angle here, right?
Yeah.
Now the faster my mouse moves, the faster that angle opens up, right?
Yes.
The slower my mouse moves, the slower that angle moves, right?
Yeah.
Okay? So what we're going to be, that angle is continually changing here, right?
Yeah.
Does that make sense? If you can visualize that initial ray here, the angle between the initial ray and the cord is always changing.
He's gonna hit himself.
So that, there we go. So that angle, the speed in which that angle opens up is called angular velocity. Does that make sense? So those of you in physics, you've been talking about angular velocity a little bit?
Yeah, we have a
Okay?
little bit.
Last class said it kind of blew their mind. They didn't know what it was until I explained that. Okay? So it's how fast that angle is changing. How fast, if we're thinking about like a tack on a speedometer on our car. How fast, when I hit the accelerator, how fast is that tack moving? Okay? Is essentially then how fast that angle is opening up. Okay? So we'll talk about that stuff in detail tomorrow. I'll get some examples and that stuff.
This thing got so bad you want to open it.
Shut up, Blaze! Sure, you don't look at me.